Welcome everyone. This is chapter 22 of the Crystal Clear Electronics video series. This chapter of the curriculum is on analog signal processing or ADC. We present it in 3 separate videos. Today's presenter is József Domokos, lecturer at Sapienta Hungarian University of Transylvania, leader of the Crystal Clear Electronics study group at Bolyai Farkas Secondary School.
Thank you very much for the introduction to Zalán Gyuricza, a student at the Budapest University of Technology. Before we get into chapter 22, I've brought a sensor data collection system, which I'd like to present briefly. These are the sensors, and this is the central data collection system. This system can measure temperature and humidity on 8 channels. It can monitor the temperature of refrigerators, for example. This is a sensor in my hand. 8 of these can be connected to the system. This system, ordered by a company, was designed for a state exam thesis. The device can log the values of 8 sensors, read them in multiplexed, and use an analog to digital converter. The sensors send the data via SPI communication protocol to a Raspberry Pi computer, which saves the values in a database. The values can be accessed via a web interface and queried in table or graph form. This device is related to today's topics in such a way that most of the time sensor data, of course if we're talking about analog sensors, can be read into a microcontroller using an AD converter.
Now, let's get into today's chapter. Chapter 22 was written by Erzsébet Szomorú Ozsvát and revised by Gábor Proksa and Gergely Lágler.
We often face the problem in real life where we want to measure some physical quantity, like what is the temperature, how noisy the street is, what color a petal is, or how tall someone is. These values usually vary in time. If we measure them continuously, these quantities can be represented by analog signals. An analog signal is a continuous physical quantity that is a continuous function of time. This means that the analog signal takes a value at any given moment, and this value may even be different at any given moment. We want the measured values to be displayed, stored in a user-friendly format, or to be transmitted to other devices such as a computer, microprocessor, FPGA, etc. for further processing. Since these devices operate with digital signals, therefore analog to digital conversion is essential for processing analog signals. Generally, the analog signal is a voltage to which a number is assigned, so the signal is converted to a series of numbers. A digital signal is a signal that consists of a discrete set of values, so it can only take a finite number of values. The figure shows the continuous analog signal in green and the digital signal taking discrete values in red. In practice, we always have to make a trade-off when mapping analog signals to digital because we need to choose the range and accuracy of the measurement. Of course, when measuring something, we want to approach the real value as closely as possible, so we want to minimize the difference between the real value and the measured value. In other words, the measurement error. The range also determines the accuracy of the measurement, i.e. the resolution. We can see that it is important to know the parameters of the signal we want to measure in order to select the appropriate measuring device. For example, even though we see the temperature rise on the mercury display of a traditional outdoor thermometer continuously, due to the scale, the temperature can be read only with the accuracy of 1 degree Celsius or 1/10 of a degree Celsius. We are trying to describe a continuous quantity by its discrete value, that is, quantize it. As shown in the examples above, many signals are not available in the form of an electric signal. In such cases, it has to be converted into an electrical signal using appropriate transducers or sensors. See the chapter on sensors for more details. Then, this continuous electrical signal is connected to the input of an analog-digital converter, the ADC. Usually, the signal range can only be positive, but there are also bipolar converters that operate in the negative range as well. The ADC is a converter which converts the continuous electrical signal connected to its input to a digital signal, and the digital equivalent of the analog signal measured periodically at the sampling time appears on its output. The figure shows a signal connected to an ADC input in green and the signal appearing on the output in red. Time is on the x-axis and the signal value is on the y-axis. After marking the maximum of the signal range, the range is divided into 8 equal parts. The measurement range is the range between the minimum and maximum value of the signal to be measured, in which we want to measure with a certain accuracy. The digital output shows which small range interval the measured signal falls into. For example, a value of 3 means that the output is in the third interval.
Why have we divided the measurement range into 8 parts?
Thanks for your question. Here, for the sake of example, we took 8, which is the third power of 2. Usually, AD converters use values higher than that, but always some power of 2, for example 2 on the 8th, 256, or 2 on the 10th, 1024. This example highlights several problems. First of all, the signal we received does not look like the input, the shape is different. The figure shows that the peak amplitude of our input signal is greater than the maximum of the selected measurement range, so the output signal went into saturation, which means it has reached the highest possible value. This phenomenon indicates that the full scale of the selected ADC, that is, the maximum input analog voltage the converter can measure without saturation, is too small. We can distinguish between two types of ADC. Unipolar ADCs can measure between a reference voltage and ground, while bipolar ADCs can measure in a symmetric range around ground. The Atmel microcontroller used in our measurements also has an ADC peripheral. On some of its pins, we can measure and digitize the voltage appearing there. The microcontroller datasheet indirectly reveals that it is a unipolar ADC because it has a pin called analog reference, the AREF, which stands for the ADC analog reference voltage input pin, and only a positive voltage can be connected to that pin. We could decrease the distortion by measuring more frequently, increasing the sampling frequency, thus reducing the sampling period. The waveforms with a higher sampling frequency are shown in figure 2 in the documentation. The horizontal axis shows that we sample the analog signal at smaller intervals. Another way to decrease the distortion is to make the intervals on the y-axis smaller, as you can see it in figure 3 in the written material. The number of intervals is called resolution, which shows how many different values the analog input signal can be converted to by the device. This is usually given by the number of bits. In our example, the 10-bit ADC has a resolution of 2 on the 10th, so it divides the measuring range into 1024 equal intervals. If the reference voltage is X, then we can measure with X divided by 1024 volt accuracy. This brings us to the next important concept, the LSB, which stands for least significant bit. The LSB shows the smallest difference in the input voltage needed to change the lowest bit of the output, i.e., it is the voltage of a digital step.
Amelyet a kimenet legkisebb helyértékű bitjének a megváltozásához szükséges, vagyis hogy mekkora egy digitális lépcsőhöz tartozó feszültség.
The LSB can be calculated using the following formula. LSB equals kT divided by 2 on the power of n minus 1, where kT is the full scale and n is the number of bits of the AD converter. Let's see an example. Calculate the LSB, or least significant bit, of a 10-bit ADC if the reference voltage is 5 volts.
LSB azaz a legkisebb helyértékű bit értéke. A mi esetünkben a kivezérlési tartományunk az 0-tól 5 volt.
The input range is from 0 to 5 volts, so the kT we just saw is equal to 5 volts, and the number of bits is 10.
Tehát az
So the LSB is equal to 5 volts divided by 2 to the 10th minus 1, so 5 volts divided by 1023, which is approximately 4.89 millivolts.
From the previous example, it is clearly visible that ADCs have to be selected carefully.
In reality, an engineer must always pay attention to price as well. The more accurate, higher resolution analog to digital converter we choose, the more expensive it will be. And for high volume devices, this is a very important aspect.
Let's look at the different operating modes of ADCs, especially the ADC in the ATmega16A microcontroller.
A detailed description is given in chapter 22, called Analog to Digital Converter of the datasheet. The first one is the asymmetric mode, which means that the voltage measured on the input channel is relative to the reference voltage. In this case, separate signals can be connected to each input pin. We will use this mode for the measurements used in this chapter of the curriculum. The other mode is the differential or symmetric mode, where the input signals run on 2 wires instead of a single wire. This is especially important for high-frequency signals, which are above 1 to 10 MHz, to avoid unwanted noise. The consequence of this is that we cannot utilize each wire individually, but only in pairs. If more differential channels are required, then another type of microcontroller or an external ADC should be chosen.
And this brings us to the end of the first video. In the second episode, we will try the ATmega AD converter in practice. Bye!
Bye!